Welcome back. So we are discussing second generation Schumpeterian models. The version I'm going to show you, I think, is in Aghion and Howitt's textbook. I will discuss the main properties of such model, and just to show you some fundamentals. Now, in this version, we have this discrete time framework. Okay, so time passes. You may imagine that this is generations, or basically each year. So it doesn't really it doesn't really make any difference for the type of analysis we are going to do. So there is this one final good. Okay, that final good sector is competitive, as in the earlier case. There is this labor employed by this sector, okay, and there are intermediate inputs, XITs, right? Remember that there are some XITs in the economy. Now, each of these intermediate inputs come with a productivity level, okay, and the innovators on the vertical innovation side will try to improve these AI measures, okay. And there is also this number of intermediate inputs, MT, right? Now this part is new. So this part, this term is new. Why is that term here? Well, we want to sterilize another effect. So this is the law of, this is called law of variety effect. Okay, so we can actually pursue, we can actually proceed without putting this term here, but studies suggest that the number of firms or the number of intermediate inputs, the product varieties, this itself should be sterilized. Okay, why? Because if we do not put that term, just increasing the number of firms will create very fast growth. All right, so to understand it, you can actually visit Barrow and Salahi-Martin's text. So Barrow and Salahi-Martin. So this is a growth textbook. I think it is 2002. So it's a textbook itself. So we put this term because realize that once we take this integral, the number m will already be there, right, on the numerator. So we divide it by mt 1 minus alpha to sterilize that law of variety effect. Okay, but it's not a big deal. Okay, it's not hugely important. So alpha is between 0 and 1, obviously, it's the capital share. Now, horizontal innovation is there. So this is horizontal innovation. Okay, now let me explain that. So this is a difference equation, obviously, right? And it tells you how the number of machines or the product varieties change. Now, this is the, so this one, in the earlier paper, we assumed this, right? Remember. And I told you that this is the simplest way of understanding horizontal innovation, right? Now, this is the second simplest way. Okay. So here we assume that N is population. Okay. NT is, let's say, population in the economy. Or, I mean, you may imagine that this is working age population. Okay. So each person has a likelihood or probability of becoming an entrepreneur. Okay, that's totally serendipitous. Okay, so in my spare time, I deal with technology, right? So maybe I open a firm, maybe I try to produce a machine that is relevant for final good productivity, right? The production of the final good. So that parameter PC is the entrepreneurship parameter. Okay, so this one is probability of becoming an entrepreneur. Okay, so what happens at each period? Some people actually become successful innovators, successful entrepreneurs, and they open firms, right? So that increases the number of firms. In the meantime, some machines drop out of usage. Okay, so epsilon is also between 0 and 1. You may imagine that this is the exit rate. Okay, so some machines produced by some local monopolies basically get out of use. All right, one reason could be that once new machines are introduced, the old machines are becoming useless. So technology changes in that particular sense, okay? Or you may imagine that there is some competition by outsiders. Those type of competition would also replace some machines, okay? The idea is that if you think about what is M in the data, you may instead look at the number of firms, right? And in reality, some firms always become liquidated, right? So they go bankrupt, they close down, etc. So this law of motion, if you think about this carefully, this law of motion you have mt plus 1 minus mt psi nt minus epsilon mt, right? So if population grow at a fixed rate, right? Let's say 1 plus n nt, then what do you have? Well, the growth rate of the number of firms will be what? Will be psi nt mt minus epsilon, right? So if there is a particular equilibrium level, what do we require? Well, we require that the growth rate is 0, right? So in that particular steady state, you have nt this being equal to 0. So you have nt divided by mt equals epsilon divided by psi. Okay. So the second simplest version converges to this logic, right? Remember that from the earlier paper. Ft equals eta lt. If you remember that, so this is now your mt, this is now your nt, right? And eta is depending on epsilon and psi. Okay. So you can actually draw the phase diagram, right? If this is n, this is m. So if n has a particular steady state, nt goes to 0, let's say, right? So then this means this means n goes to n star. Then you have this other equation for delta m being 0, right? So there's a steady state, and that steady state you can actually show that it is a stable node. Okay, so you know these tools, and you can actually studied that stuff. Okay. So that's the horizontal innovation part. Okay. Again, this is the simplest way of thinking about this. In week 11, I guess, when we are looking at the Pareto's paper, 2015, I guess, then we're gonna understand such horizontal innovation in a fully endogenous way. Okay, so we're gonna find how new firms enter, how new firms are established through a technology, an entry technology, right? So there's an underlying industrial organization theory of this. So that's the horizontal innovation part. The vertical innovation part. So this is the vertical innovation part, right? That's already familiar. I mean, you are already familiar with that. We discussed this last week, right? So there is, in each sector, for each intermediate input, there is a monopoly firm that already produces the given version of it, and then there is this competition, right? So there's another monopolist out there who tries to innovate the new version. Okay, so the targeted productivity is this, right? And this is the success probability, as we discussed last week. So the success probability will be a function of normalized research spending. Okay, and here we put decreasing returns with respect to R&D spending, but there is no decreasing returns with respect to knowledge, right? So in the Jones paper, make the connections. In the Jones paper, there is that fee parameter here. Okay, right? That fee parameter in the Jones paper is here. So we don't do that. There is no fee parameter here. So I mean, if you really want to put fee parameter here, you have to assume that fee is equal to 0. So there is no decreasing returns with respect to knowledge. Okay, so no decreasing returns with respect to knowledge. Then of course, there is also a failure probability. Okay, now that probability depends on your normalized research spend. So RIT is the total amount you spend, and lowercase r is the normalized one, right? So AIT star is the targeted productivity. So this is AIT star. Okay. Now remember, how do we solve this model? So we first normalize this price to unity, right? The final good price. Then we maximize this profit right by choosing machines and labor. Okay, so that's the final good firm. Then existing monopolies maximize this, right, by choosing X. But of course, price depends on certain factors. And in fact, we realize that price will depend on how large the final goods sector relative to the number of firms. So that's the important variable in such models, firm size. Okay, so the innovation decisions will depend on this. Okay, so in the earlier version, when there is no horizontal innovation, the firm size was basically expressed in this particular way, right? So price, remember, was depending on LT and other stuff. So that's because there was, I mean, that's the reason why there was a scale effect. But now, firm size, I mean, labor is normalized, okay? So we are looking at each and every particular innovating firm in the economy, or the number of firms, or the number of intermediate inputs over which innovation continues, and the firm size is normalized by this number of firms. So as long as the number of firms increase, the scale effect will be sterilized. Okay, so that's the logic, and that's the beautiful, that's how the second generation models actually sterilize the scale. Now, as you know, after finding X, you go from this to profit. Okay, so each sector there is a profit level. Then the R&D firm maximizes expected payoffs, right? So there is probability. This is success probability. This is the profit minus total spending, right? So this is A star. Okay, and this firm, this R&D firm, chooses R. Now, after solving this, of course, that depends on other stuff. You basically find that optimal R, okay, the optimal R will be a function of that firm size, which does not depend on. So you can do the math here. So you can do all of this by using the tools you learned last week. The end result will be that this is of course positive. So if relative to the number of firms, if labor force is larger, then firms spend more in R&D, but that will be constant for all I and all T. Okay, so this then allows us to, use the law of large numbers. Remember last week again. And then average productivity. Now, average is defined in this way. So the average productivity is defined, of course, in this way. Okay. Then average productivity will grow. Okay. So it will grow in that particular rate. So it will be depending on mu star gamma minus 1 minus 1. So let me double check. Maybe I'm mistaken there. Where's that? I'm looking at my paper in the meantime. And I cannot find it. Sorry. Yes, okay. That's not correct. It will be gamma minus 1 plus 1. Okay, and it will be, sorry, it's not correct. So it will be like, okay, let me do it in another page. So once you solve it, AT the average will depend on this, okay, times gamma minus 1 plus 1. Okay, so percentage growth rate will be C RT rho gamma minus 1. Okay, so that will be the percentage growth rate, and RT will be a function of the firm size and the derivative of R with respect to LM will be positive. Okay, so that's how, after applying law of large numbers, of course, there are some successful sectors and there are some unsuccessful sectors, but on average, productivity will keep improving at this particular rate depending on the probability of success and the step size. Okay. Now, of course, in that particular problem, you can introduce policy, right? So the problem was this, right? Now, if you want to introduce subsidies, research subsidies, right? So these are research subsidies. This is research subsidy rate. So you can actually do it in this particular way. And if you solve this, RT, of course, will be depending on not just the firm size, but also to research subsidy rate, and the research subsidy will have a positive impact on the growth rate of the economy. Okay, so another thing that you can do is to extend the model with human capital. That's basically what I do in my paper. So instead of, so when you write this in the simple version, you have a couple of options. First, you can suppose that everybody works, okay? Then you can suppose that everybody works a particular hour, okay? So UT is between 0 and 1, okay? You can also suppose that when people supply labor, they supply their time and also they supply their human capital. Okay, and human capital would be, so H here is human capital. U here is hours worked. Okay, and then in such a framework, if H continues to grow, okay, you have to sterilize this effect as well. Okay, then in your model, you normalize your research expenditure in this particular way. So this is the total expenditure. This total expenditure will be normalized by human capital and the targeted productivity. Why? Because otherwise there is no balanced growth path, as I will show in my paper. Okay, and there could be perhaps other ways of doing such labor market clearing, right? So this is basically labor market clearing condition, right? So this is supply, this is demand, or this is supply, this is demand. Okay. So in that particular paper of mine, I of course want to study many different sources of growth. So I introduce human capital, but in the simplest model in the textbook, there's no human capital. So let me just show you a couple of figures and conclude today's lecture. Do you have any questions about the model? Okay, if you have no questions, let me show you a couple of figures and then we are good to go. So there's the paper. So this is my paper, the published version. So first, let me show you the growth rate. If you find the growth rate in this economy, okay, so growth rate depends on these parameters. As you see, it is highly complex, okay? Now, some of these parameters are preference parameters, okay? ETA is a human technology, ETA and new are human capital accumulation parameters. Phi and lambda are preference parameters or utility function. Alpha tilde depends on alpha only, so that's another parameter. As you see, epsilon and psi is there, so these are horizontal innovation. And as you know, rho, xi, and gamma are vertical innovation parameters. So the entire set of parameters that explain long-run growth rate are many, okay? So this is the long-run balanced growth rate of the economy, all right? And each of them has a particular meaning, a particular functioning, all right? For instance, this is the long-run firm size, right? So L divided by M goes to epsilon divided by psi. This is hours worked per worker, okay, this parameter. And these human capital accumulation technology parameters appear here, as you see, because the model must have a balanced growth path between growth rate of average productivity and growth rate of human capital, okay? But once you study this model, you're going to understand the logic much more clearly. Let me show you a graph. Yes, this one. As you see, in this model, population itself will grow until it reaches a steady state. Okay, so let me clear these things. So there is a particular law of motion for population, and that law of motion is stable because there is a time cost of fertility that changes with population itself. So when population is getting larger and larger, the cost of producing new babies is getting larger and larger. So there's a stable population growth in the long run. At that level of population, there is this firm size depending on the entrepreneurship parameters, okay? Then, of course, I discussed how I use the data for Turkey as well, but this is how you judge the model's success, okay? The model explains a couple of stuff. One is total fertility rate, okay? And these are non-targeted moments. So I will explain this next week when we start discussing quantitative tools. So in this model, I try to match the growth rates, and there are some other variables that I can use to judge the model's explanatory power. One is total fertility rate. As you see, it is not exactly overlapping, but still very successful in understanding the change in fertility. So the black line is the model. The squares are the data, okay, for Turkey. This one is the stock of firms, log million. So the stock of firms increases both in the data and in the model and in a concave graph. So that's also is a non-targeted variable. Since it is non-targeted, I can actually use them to judge my model's explanatory success. And finally, little less successful is the total population, okay? And there is a good reason why the total population is not particularly successfully matched in 1955 and 1975, and I explain in the paper. But overall, the goodness of it is not that bad. Then this is your model simulation result. As you see in Turkey, the model. So this is GDP per capita's growth rate in the data, and in the model, kind of explain this through the growth slowdown in many variables. This one is physical capital. This triangle is the stock of firms. So these are growth rates annualized. The square is average productivity. As you see, there is productivity slowdown in Turkey. Okay. The only thing that grows and explain the growth of GDP per capita in Turkey to a large extent is human capital, and according to this model, as you see, the contribution of human capital will be getting larger and larger. Okay, the contribution of human capital will be getting larger and larger. So again, in your last assignment, you're going to replicate these findings. I can share you some codes. So don't just worry about it, but you have to understand the logic behind all this. Why am I showing you this right now? Because this is a second generation Schumpeterian model, essentially. Okay. So let me now stop. So if you have questions, we have 3.5 minutes for me to reflect on that. Okay, let's see what we are going to cover next week. So next week will be our 7th week, and we're going to look at this very nice paper by Kydland and Prescott, published in Journal of Economic Perspectives in 1996. So the purpose of next week is to introduce some quantitative tools, okay, such as calibration and simulation that I expect you to learn, and I will show you a lot of stuff. So it will be, a full 3 hours perhaps. But then those tools are necessary, and you have to pay attention. I will post the paper for you to read before class. Okay. and we continue. If you have no further questions, I'm gonna end this session. Okay, great. So see you next week then.
Okay, thank you.
Bye bye.